Okay, so I believe everyone should already seen my announcement regarding the final exam. So pretty much the format is more or less the same. And so basically the only difference essentially is that, first of all, of course, the time will be longer, right? So as I said, I mentioned in the announcement that it will be 130 minutes. So essentially I designed the exam to be 105 minutes and plus another 25 minutes scanning, because I understand that this time the exam is longer. So you might have a little bit slightly more papers to scan. So I give you a little bit more time, but definitely the same rules, right? Like you only have 130 minutes. And I opened the window from 12:45 to 3:15. So like in case some people may have some exam right before, right after. So so our original schedule time was 1 to 2:50, but then I kind of essentially make the window a little bit longer. So hopefully that should accommodate that whoever may have exam a little bit before or after. So if you have any questions regarding the time or the rules, please let me know, then I could explain to you. But definitely what you want to do is to read the instruction carefully, which means that you're going to only have 130 minutes. And of course, like you should make sure you submit every pages. Like if you miss something, right? If you forgot to submit one pages or something like that, then I will have to take it as it is. So definitely make sure you read the announcement carefully. And as I also mentioned that I already posted a review note and with some blank example, and there's already a short solution provided there. So you should start working on it until maybe Thursday. I will go over the note. So, but you definitely still have time over the weekend to go through those problems, of course. So a little bit later, I will post the detailed solution for this note. Probably it's better probably after the review. And also for the final exam, it's comprehensive, meaning that I'm going to cover everything that we learned from this semester. But as I mentioned in the announcement as well, I'm going to focus on the new material in the sense that at least 50% of the exam problem will come from the new sections, which I listed the section there. And it's going to be up to section 6.1. And I understand that we only have limited time for covering up 6.1. So what I'm going to do, as I mentioned in the announcement, is that because we learned eigenvalue and eigenvector problems, and but of course it's possible to have complex number as an eigenvalue, but just to keep the problem as easy as possible. So I mentioned in the announcement that I'm going to only test the case when there's only like a real value for eigenvalue. So you don't need to worry about the complex case. Even though in today's class, for the completeness of the material, I will still cover the case for complex value. So people will know that actually, indeed, you could possibly have complex value as a eigenvalue or eigenvector. But I'm not going to test the complex case in the exam. And also for the section 5.1 for the scalar product, like we only cover very limited for scalar product. So I also mentioned that the only point for 5.1 this time is really, what's the definition, how to compute the scalar product. And most importantly, to use the scalar product, for example, to know how to decompose a vector into two perpendicular vector. For example, that's what we call the orthogonal decomposition. So that would be the main focus for 5.1. So that's it. And then don't forget that the homework 11 is due on Friday. So I extended the day. So there's after today, I believe that like I will do some problem that's going to help you on some of the problems for the homework 11. Okay, so any question so far? Okay, so by the way, this one thing just occurred to me that like because right now we pretty much have most of the homework scores back. So do me a favor, right? Like check through all your homework score in the sense that if you have any questions, like for example, if you feel like that there's discrepancy between the score you got and the score recorded on the Blackboard, please let me know. Or if you have some question regarding the homework score, please let me know. Either send me an email like, or you can make an appointment with me, or actually come to the office hour from 1:30 to 2:30, because it's almost reached the end of the semester. So if you have any question regarding, for example, the past homework score, you should definitely let me know before I start calculating everyone's grade. And for the regarding the homework 11, because it's due on Friday, so pretty much over the weekend, right after I got everyone's homework, I'm going to post the solution so you can actually use the solution to review for the final exam. Okay, so so that's recall what we have defined last time. So I'm going to quickly go over the definition for eigenvalue and eigenvector. So last time we say, okay, because later on you're going to see we're going to take the determinant of the matrix. So if you have, so we are only consider the square matrix in this case, and the eigenvalue we use like lambda always for the eigenvalue. This is kind of the convention that mathematician did. So this scalar number is called an eigenvalue of the matrix A if you can find a non-zero vector, right, such that A times X, the effect of A acting on X, will equals this specific scalar value lambda times X. If you can find such X such that this equation is true, then we call lambda to be the eigenvalue. And the vector X is what we call the eigenvector associated to this lambda. So because we say it's associated, so as you can imagine that for different eigenvalue, you will have different eigenvector, right? And actually, don't forget that last time we also mentioned if you have a, say, if you could find such eigenvector, say X, right, some non-zero. Okay, so I want to highlight that it has to be non-zero. So so if it's not, if it's zero, then it cannot be the eigenvector. And if you could find such eigenvector X, then it turns out that for the same eigenvalue, right, you have an eigenvalue, you have the corresponding X, right? It turns out that if you multiply this X by any non-zero number, right, then the new vector, if I call it V, for example, this new vector, which is a multiple of your original eigenvector, is also an eigenvector of lambda, associated with lambda. So it turns out that if you can find one, then any vector along the same line as this vector will still be an eigenvector. So eigenvector is definitely not unique in the sense that if you can find one, then any non-zero multiple of this eigenvector will still be an eigenvector associated with the same value. So you can see that then the collection of all the eigenvector in some sense should be like some kind of subspace, right? It should be infinite many vector. It might be one-dimensional subspace. It might be two-dimensional. Depends on how, like, what the eigenvalue looks like, or depends on the matrix. So we're going to see a little bit more example. Then the question we discussed last time is how do we find the eigenvalue and then also the associated eigenvector, right? So to find the eigenvalue, we essentially want to be able to find such vector X first, right? And then it turns out that last time we discussed it. I don't want to repeat too many detail. You can actually check my notes or the video last time. So it turns out that it boils down to solving a polynomial. And the degree of the polynomial depends on what's the dimension of your matrix. For example, here, if you say the matrix is n by n, then it's an nth order or nth degree polynomial, right? So this is what I put here. It's nth degree polynomial. And the polynomial we're solving, it's a polynomial in terms of lambda, meaning you might have something like lambda q plus 2 lambda plus 1 equals 0 to solve, right? So you want to solve this determinant of a minus lambda I to be 0. Because if this is 0, then this matrix is singular. Then you're going to be able to find the non-trivial vector in the null space of this new matrix. And that's the eigenvector we are looking for. So basically, you form this polynomial. This is, you can call it P of lambda. This is what we call the characteristic polynomial. And you want to solve this polynomial equals 0. And whatever the root you're going to find is the eigenvalue. So this is just a quick short review of what we have done last time. And once you find lambda, right? So basically you first solve this polynomial equals 0, you find several roots, right? And you're going to have nth root, right? But you have n in total n roots discounted. This also include the repeated root. For example, if you have degree 3, if it's 3 by 3 matrix, you could possibly have 3 eigenvalues, for example, when the first one is 2 and the second and third one are all 1. In this case, we're going to see an example later on, you could have repeated root. But of course, when you solve some polynomial equals 0, it's possible that we don't have real number as the root. So this is the case when it comes to the complex root. So depends on how much time we left today. I mean, I really want to be able to at least demonstrate one example for complex root, even though it's not on the exam coverage. So now, once we find the eigenvalue, then we want to essentially the eigenvector is in the null space of this matrix. So basically, the null space, what's null space? It's the collection of all the vectors such that a minus lambda I times x equals 0. And this x is exactly the eigenvector we are looking for. So you can think of eigenspace is the collection of all the eigenvectors, right? And that's why once we found lambda, we are going to solve the null space of a minus lambda I. Whatever the things we found, those are the eigenvectors, right? And then because it's a null space, so you can imagine it's a subspace. So we should be able to express this subspace in terms of, say, span of some basis vector, right? Depends on how you want to describe it. Okay, so that's the general scheme that we have done last time. So I remember last Thursday, I started kind of do half of the problem. So I want to quickly review how do you find the eigenvalue. So we have this 2 by 2 square matrix. I want to find the eigenvalue and its corresponding eigenspace. Okay, so first we want to solve like what we did, like the characteristic polynomial. So we want to solve determinant of a minus lambda I to be 0, right? So what's a minus lambda I, right? I is the identity matrix. So A is 3, 2, 4, 1 minus lambda times identity matrix. So you will see that it's really just the diagonal or lambda, and the off diagonal is 0. So this will essentially just be 3 minus lambda 2 and 4 minus 0, 4 and 1 minus lambda, right? This is the new matrix. Okay, so now we want to solve determinant of this matrix to be 0. Right, so we really just calculate it. So you can see that's how we form the characteristic polynomial. Right, so you have to expand the whole thing. So this would be lambda squared minus 1 minus 4 lambda plus 3 minus a. So you want this to be 0, right? So if you stare at this, most of the time it should be able to do the nice factorization, right? So this turns out to be, you can decompose it into factorize into lambda minus 5 and lambda plus 1 equals 0. So last time we have actually seen this already, but I just want to repeat. So we know that we have 2 roots, because essentially that means we have 2 eigenvalues, okay? And as I mentioned last time, if you want to solve this polynomial equals 0, if after say 20 seconds, you really couldn't see how are you going to factorize it, just directly do the quadratic formula, right? The quadratic formula will always guarantee that you get some answer, right? So instead of, if you really say are not comfortable or are not good at trying to factorize this kind of polynomial in short period of time, just directly do the quadratic formula if you feel quicker to do that way, right? You don't have to like trying to figure out for like a whole 5 minutes or 3 minutes trying to figure out the factorization, right? There's other way to solve the root here. Okay, so now we have 2 eigenvalues. So you can imagine we should have 2 corresponding eigenspace. Okay, so the first thing, I don't want to repeat the thing I already done for last time. So I already included some of the detail here. So first, because I called this, it doesn't really matter which one you call it, lambda 1 or lambda 2. This is just for convenience. So I first already found the eigenspace for lambda 1 equals 5 for the first eigenvalue. So the eigenspace, again, it's the null space of A minus lambda I. In this case, because I first focus on the eigenvalue 5, so I want to solve the null space of A minus 5i. So again, the solution in the null space is going to be one choices of eigenvector, right? So we want to solve this null space of A minus 5i, right, when lambda equals 5. So, I mean, you really just take A minus 5 times identity, right? This is what we do here. Then you got this matrix. And as you can see, you can do the Gauss elimination, right? And trying to solve the trying to reduce it to either REF or REF, right? So you can see that you can do the reduction to this nice matrix here. And so basically, eventually you got this 1 minus 1, 0, and 0. So I'm solving for the null space. And from here, I mean, you can see that, so the pivot is at x1, right? So x2 is, I call it alpha. And in this case, x1 will equals to x2 equals alpha when you're trying to solve the null space. So basically, all the solution in the null space looks like some random number alpha times 1, 1, right? So we know that the null space is the span of 1, 1. And this is essentially the eigenspace for this particular eigenvalue. And if you ask me, then what would be the eigenvector looks like if I want to be specific, say, so I already solved, depends on what the question is asking. I'm asking for the eigenspace, right? So this is the eigenspace. But I might ask you, say, or the problem in the homework might say, find the basis, right? So in this case, you can see that you can be, like, depends on how you want to answer the question. You can say basis for this eigenspace is this vector, right? Because we only have one basis. But if I can ask you a little bit more conceptual question, okay, then what would be a possible eigenvector, individual eigenvector, right? So one example, so that I want to make a remark here is that from this expression of null space, it tells you that any vector in this form, right? Because we solve the x to be alpha, alpha, right? So any vector in this form, I should be careful, any non-zero vector in this form, right, can be an eigenvector of this eigenvalue, right? So for example, it could be, I don't know, pick the number you want, right? -2, right? Or you want like √5, doesn't matter, right? As long as it's in the format of alpha, alpha, then this is one of the eigenvector. Then you might ask, how am I going to check my solution, right? So you can actually double check, for example, I claim, and then you already tell me basis is 1, 1, right? So 1, 1 should be able to be one of the eigenvector. So you can actually check, right? If I claim 1, 1, say it's an eigenvector, right? Or because it's a basis of the eigenspace, so it has to be one choice of eigenvector. So you want to say, okay, I'm going to take A times 1, 1, for example, right? So A is 3, 2, 4, 1 times 1, 1, right? You can see that this is going to be 5, 5, right? After you mod, and what's 5, 5? This is essentially 5 times 1, 1, and this is my eigenvalue, right? So you can see that 1, 1, which is the basis you just found, is indeed one of the eigenvector, right? Because it satisfies A times X equals lambda X. So that's actually one way you can check your solution, right? Because if you found some basis, that basis must be an eigenvector, right? If it's not, then you found the wrong basis for your eigenspace. So I sometimes really insist of this type of checking, because when you know how to check your answer, that's when you really, really know what you're doing and understand the concept. Okay, so this is one of the eigenvalue, right? So the other ones, I'm going to solve the eigenspace for the other. So which one is so the other is -1. So for the second eigenvalue, right, -1, right? So I want to find the null space of A minus lambda I, but now lambda is -1. So I want to do A plus I, right? And let me just calculate the A plus I first. So A is 3241 plus identity. So this would be 4242. Okay, not too bad at all. Okay, so I want to solve the null space of this matrix. So I want to find all the solution that satisfy A plus I times X equals 0. Okay, so really solve the null space as usual. Okay, so I mean, this is kind of silly because you can see that this is the example becomes like almost immediate. So we can cancel out the second row. And I want to be able to see the solution more clearly. So I divide it by 1/4. I mean, you don't have to, but I just kind of want to simplify a little bit more. Okay, so you have 1/2 and like that's essentially the first row. Okay, so now let's solve for the solution. So this is the pivot. So x2 would be again alpha. x1 would be minus 1/2 x2, which is minus 1/2 alpha. So my solution will looks like minus 1/2 alpha. So the basis is minus 1/2 and 1. Okay. So this tells me that any vector, any eigenvector should looks like a format of minus 1/2 alpha times alpha, and alpha can be any number, right? Except 0, right? I should be careful because that's when we say it's eigenvector. Can be any number but 0. Okay, so then we know that the eigenspace of this eigenvalue is essentially the span of minus 1/2 and 1. Okay, and of course, if you want to answer the question what the basis is, then the basis is just this one vector. Right, so it's actually not too bad at all, right? Like, as I said, right, once you know what you want to solve for eigenvalue and eigenvector, the techniques of solving it, you already knew it, right? It's really, first you solve some algebra, high school algebra, right? Finding the roots of some polynomial. And second, you need to find the null space of some new matrix, A minus lambda I, right? So that's why you really have to know how to find a null space of some matrix. If you don't know how to do it, then you are in a big trouble, right? Because a lot of questions involve doing this kind of procedure. Okay, so any questions so far for this problem? Okay, so you can see 2 by 2 is not too bad in the sense that this only at most 2 eigenvalue, right? And so it's actually hard to show like the repeated case. So in the next example, I want to show you like a 3 by 3 case. So as you can imagine, 3 by 3, because it's larger, right? Like, so you need to do a little bit more work in the sense that when you find the eigenvalue, the polynomial become cubic. So I remember in the homework, you might actually see 1 or 2 problems that's about 3 by 3. It's either 3 by 3 or 4 by 4. So you want to be a little bit patient with the algebra here. So same thing, right? So I mean, procedure is exactly the same, but I just want to show you what's the possible other situation that you might encounter, right? So again, find eigenvalue and the corresponding eigenspace. So first step, right? Solve eigenvalue, right? And the way we solve it is really by solving determinant of A minus lambda I to be 0, right? So now let's see. So I'm going to directly show you what's the determinant, the matrix here. So just keep in mind, right? You want to take the matrix minus lambda I. It's just lambda times the identity. So in some sense, long and short, you just really only need to minus the lambda for all the diagonal entry, right? So you can see the only thing that's going to get affected is really the diagonal entries, right? And then all the other entries are the same. right? Okay, so this is the A minus lambda, and I want to solve the determinant. So unfortunately, this matrix is not that pretty. So I mean, you just need to expand the determinant. So what I'm going to do is expand along this first column. Okay, so let's see. So 2 minus lambda, right? And so you want to be a bit careful here about the algebra. Okay, so plus minus 1 times, let me see. So this would be minus 3, 1, minus 3, 2, minus 1, and plus. Okay. Okay, so this is not too bad. So unfortunately, you just have to expand everything. So you have 2 minus lambda, and this part you have minus 2 minus lambda times 2 minus lambda plus 3. And minus, this is minus 3 times 2 minus lambda plus 3 plus minus 3 minus 2. Okay. So there's actually, unfortunately, no shortcut in the sense that regarding this type of problem, you just have to expand it, especially because you can see the matrix is actually not ideal at all, in the sense that when you're trying to solve the determinant without expanded, right, you cannot really find what's the final polynomial looks like. So I'm going to skip a little bit step because this is really just a pure algebra. So expand the equation, right? So if you expand it, you should cancel out several other terms, right? There's some other cubic term, right? And there's some other lambda square or constant. So you need to expand everything and simplify. Okay, but once this problem, of course, at the first sight, it looks like there's no way you can simplify. But really, after you expand everything and cancel out some term, you actually eventually you should get this polynomial, and turns out to be pretty because you need to have something that's solvable in some sense. Okay, so you can see that if you can get this, right, then this is not too bad at all. They all carry at least one lambda, right? So you can actually factor out lambda. In this case, because I want to be able to see the nice factorization, so I'm going to factor out minus lambda. Okay, so in this case, it will left with lambda squared minus 2 lambda plus 1. And when you see this, you should realize that like this thing, lambda squared minus 2 lambda plus 1 is actually a perfect square. So you will end up with something like this, right? And you want to solve this to be 0. Okay, so first let me solve it, and I want to make a remark here. So then this tells you actually technically have 3 eigenvalues. First is lambda 1 equals 0, right? Second, you have a repeated root for 1. So here I want to emphasize that you need to indicate or show that there's a repeated root. So for example, in the homework, or especially in the exam, if you only say lambda equals 0, lambda equals 1, I will take some points off, because then I don't know whether you realize that it's actually a repeated root. Because technically, if it's a 3 by 3 matrix, if you want to count the roots, right, like there's a cubic polynomial, you should have 3 roots, right? So you should actually indicate that, oh yeah, you recognize there's a repeated root here, repeated eigenvalue. Okay.
Question on that.
Yeah.
By definition, the lambda can't equal 0.
Oh, no, eigenvector cannot equal 0. Eigenvalue could be 0. So, okay. Yeah. So actually, it's possible to have eigenvalue to be 0, right? So for example, you could have a non-zero vector. For example, I'm just make up some number. For example, maybe 1 or 2, right? So you could have a times 1, 2, right, equals 0 times 1, 2. That's 0, right? So eigenvalue could be 0, but eigenvector shouldn't be, right? So yeah, that's the difference. So eigenvalue could be 0. Okay. Okay, so now let's see. Okay, so yeah, so if you see the repeated eigenvalue, please indicate it by, for example, just showing me that there's 2 eigenvalue here, right? Or at least you should say something like a repeated root, right? So I need to see this evidence that you realize that you actually in total should have 3 counts, right? So you can see that this is a 3 by 3 matrix. So you have 1 count, 2 counts, 3 counts, okay? So now another thing is this example seems may not be well designed in the sense that, yeah, you need to do some algebraic work, but there's another, there might be some shortcut in the case. For example, it really depends on what your matrix looks like. This is not a pretty matrix in the sense that once you do A minus lambda I, the matrix is not pretty, right? Oh, so someone asked the question that how do I know 3 by 3 matrix that 1, 1, 2, 2 need to be sub, because it's A minus lambda times identity, right? So I'm taking A minus lambda identity. So what's identity? It's lambda times 1, 0, 0, 0, 1, 0, 0, 0, 1. So it's A minus, yeah. So that's why I say that technically, if you know what to expect, you can kind of skip the step. But of course, if you don't know how to skip the step, just do it step by step, right? But as an observation, I know that I only need to subtract lambda from the diagonal, yeah. But you need to be careful, right? The algebra, you can easily make mistakes. So what I was about to say is that it really depends on how messy the matrix looks like. For example, when you solve the determinant of A minus lambda, there's a, I'm going to write it down here, right? For example, if A looks so nice, right, in the sense that you could have possibly later on solve the determinant of A minus lambda to be something like this. I'm just make up some extreme example. So if you end up getting the determinant of something like this, then you can see that this is really just a triangular matrix, right? So you can see that, don't forget that this is something we learned a while ago for exam 1, right? For triangular matrix, this is upper triangular, and it doesn't matter. Maybe you could have a lower triangular. But the upshot is for calculating determinant, the triangular matrix is perfect because the determinant would be just the multiplication of the diagonal, right? So in this case, you don't really have to do the expansion that much. You know the determinant will end up to be the product of those 3. And if this is the case, you already have the factorization, right? So at this point, then you don't have to expand it, right? Because your goal is to solve this equals 0. You already, if this is the case, right, you already have the factorization. So in the past, what I've seen is that people were not thinking what they were solving. At this point, they say, oh, I got this, so I still expand it. And then when they expanded, they couldn't get back to the original factorization. So be careful that when you probably already had the factorization without even knowing it. So you really want to remember that what your goal is, right? Your goal is really to come up with a factorization so you can solve the root. So in this case, if your determinant is nice enough that you right away put up as a factorization, then at this point, do not expand it to make it worse. Okay, so this is just some common mistake I've seen in the past. Okay, so this is just an extra remark here. Okay, so now we found technically 3 eigenvalues, but 2 of them were distinct. Okay, so now we want to solve the eigenspace. Okay, so for the first one, I want to solve the eigenspace for the 0, right? For the 0, 1. So you can see that I want to solve the null space of A minus lambda I, but this time lambda is 0, right? So essentially you can see that now it becomes the same as solving the null space of A. So in some sense, you can think of that if you could possibly have an eigenvalue to be 0, then the eigenvector are exactly those vectors in the null space of the original matrix. Okay, so this is possible, right? Okay, so now let's see. So since I just want to solve the null space of A, so I don't need to really do anything to A. So let me just copy down the matrix 2 minus 3, 1. This is 1 minus 2, 1. Let me double check this is the case. Yeah, okay. So now I'm going to do the reduction. Okay, so let's see. So that's I mean, there's so many ways you can do the reduction. So I'm going to just like swap the row here. So this would be, actually, no, I want to swap this to row. Okay, so you know what? I'm going to save some time here because we have so many things to do. So this is actually, I'm going to leave to everyone to do the exercise. So you can do the Gauss elimination to reduce to REF. Okay, so I'm just going to tell you the final result because this is very standard. Everyone should be able to do it now to just reduce to REF. Okay, so I'm going to leave you to do that. But the upshot is now we do have two pivots here, right? So, okay, so let me solve this. So x3 will be alpha and x2 will be, oh, okay, alpha, and x1 will be x3, that's alpha, okay. Maybe not so interesting. So x would be alpha, alpha, alpha. So I have 1, 1, 1 as my basis, okay. So the null space, which essentially this is my eigenspace of this eigenvalue. And if you want to write it as a span, it's a span of just one vector. And the basis for this eigenspace is just this vector, right? This is the basis, okay? So this is just one of them, right? So I still have the other, okay? So the other is 1, okay? So for second and third eigenvalue, this is actually, yeah, sorry.
Sorry, just a quick question.
Yeah.
Is that where the n parentheses a comes from, is because of this property of the eigenvector values? Is that why we write the null space in that manner?
So what do you mean? Like, sorry, say again.
When you write like the null space as n parentheses a close parentheses, is that why we do that? Does it come from this? Is that where that originally spawns from? And we just cover it in the other order, or is there another deeper meaning to that we haven't gotten to? And would be,
oh, you mean why I write this, or?
Yeah. I just wondered if that was standardized because of the eigenvector stuff.
Oh, no. I think this is just a null space for every matrix, right?
Right. I didn't know if that came from when you write it as n of a minus something times I.
Okay. Yeah, so actually be careful here. In general, if we want to solve the eigenspace for some eigenvalue lambda, what we were solving is actually the null space for this matrix.
Right.
Yeah, this is the new matrix, right? It depends on what lambda is. It could be a total different matrix than A. So technically, what I'm solving is the null space of this new matrix. But since in this case, like I want to indicate that in this particular case, because I have eigenvalue to be 0. So it turns out that the eigenspace for the eigenvalue, if eigenvalue is 0, right, then essentially it becomes the same, solving A minus 0 times identity, right? So that's why in this spatial case, when the eigenvalue is 0, solving the eigenspace for this particular eigenvalue turns out to be the same as solving the null space.
Oh, okay. See, I thought that solving the null space was like
no.
That's
actually this is a good question. In general, you should solve the null space of A minus lambda I. And what the matrix looks like really depends on what lambda is. In this particular case, because I happens to have one eigenvalue to be 0. Yeah. That's why it reduced to the null space of A, but it's not always the case. In general, it wouldn't be, right? If you can imagine if lambda should be 2, that's different. Yeah.
Right.
So you want to be careful.
I thought solving for the null space for just a vector by itself just kind of clicked to me, but I guess it's not, would be the like special case of solving like eigen equations. But
yeah. So this is a spatial case. Yeah, actually someone just asked me, if they want to solve like, for example, in this case, as you can imagine, right? Because if you want to, because this is the definition for eigenvalue, eigenvector, right? If lambda is 0, right? Then you're solving AX equals 0. So that's why your eigenvector will turns out to be any vector, non-zero vector in the null space, right? So that's why this is a spatial case. Yeah, so I'm also asking the Devon's question. Yeah, it turns out that in the spatial case that when 0 is one of the eigenvalue, then you're solving, essentially your eigenvector will become any non-zero vector in the null space. But not every matrix has 0 as an eigenvalue, right? Like for example, like the first example, we didn't see any. Yeah, so that's why I said it really depends. Depends. It really depends, right? For example, you need to first find out what your eigenvalue is. Then it depends on what eigenvalue is. Then you will have a corresponding eigenspace. So yeah, that's why I mentioned this example, because there's so many spatial case that different kind of thing that you might see it before. Yeah. Okay, good question. I'm glad that people asked, so I can clear this up.
Wait, hold on. I'm a little confused now.
Yeah.
Which one are we actually solving for right now?
So I'm solving the null space of A minus lambda I. In general, that's my eigenspace for whatever the eigenvalue lambda. But I'm solving this this 3×3.
Yeah, but whenever you do the null space for lambda equals 0, you have a subtraction actually happen. But wait, why does anything actually get reduced then? Or did you just switch to rows?
Oh, no. So I'm just saying that if I'm technically I'm solving for any eigenvalue lambda, I'm solving null space of A minus lambda I, right? But in this particular example, one of the eigenvalue is 0. So when you're trying to solve the null space, which is the eigenspace, right? Eigenspace for lambda, but this time, because in this spatial case, lambda is 0. So when you solve A minus lambda times I, right? But this 0 times identity, this is just 0 matrix, right? So it reduced to the null space of A in this particular situation. Yeah.
Oh, I just realized you actually switched rows 1 and 2, and that's why I was like really confused, because I thought you subtracted like from 1 or something.
Oh, no. It's just I'm looking at A minus 0 times I, so it becomes A, right?
Yeah.
So yeah, so actually this is a spatial case. Yeah. Yeah, so that's why there's certain phenomena you should not take for granted. You should just follow the original step. Yeah. Okay, so now let me see. So okay, for the second eigenvalue, it's 1. So do the same thing, right? So you want to solve for find the null space of A minus lambda I, and lambda is 1. So I'm just indicated this is 1 times I. So you are solving the null space of A minus identity, right? So I'm going to show you what A minus identity looks like. So then give me a second. So this is A, right? But I want to minus I. So this is, I only need to subtract 1 on diagonal. So I'm doing a little bit skipping the step, right? If you're not comfortable with like combining algebra, just do it step by step, right? So you don't make mistakes. Like I've seen in the past that people want to make it quick and then like, I don't know, subtract the wrong thing from the wrong entry. Then
scroll up a little bit.
Sorry, yeah, here. Did I make mistake somewhere?
I thought the first row of the original matrix was the 1, -2, 1, which would make that first row.
Oh no, the original matrix is 2, -3, 1.
Okay.
Yeah, and I swapped it once because I was actually thinking I'm going to solve the reduction completely, but I realized that I want to save some time. So I first like swap the first row and second row. I trying to solve the null space and I stop it there. I didn't do completely solving. I'm just like, I swap it here. This is the original matrix.
Right. Now, when you get ready to do this A minus lambda I, if you've swapped the rows, do you also have to swap the rows in the identity? Because I think that's going to end up giving you a different answer.
Oh, no. What do you mean? Like, so first this is A minus
like
lambda I, right?
Right. But this, the math that you're doing here is with respect to the original matrix A without swapping.
Oh, no,
row
no, no.
one
Of
and
course,
two.
I need to do it. I need to do it with the original A. I mean, the swapping is app. Like once I found the A minus lambda I, then because I'm essentially technically solving this whole thing equals 0, right? So the swapping comes from, or actually already I'm start doing the reduction already. When I do the swapping, I was trying to do the Gauss elimination. That's why I can swap. But you need to first find out A minus lambda I before you swap, right? Otherwise, you are not really looking for A minus lambda I.
Right, and again, that's against the original matrix.
Yeah. The original matrix is two minus. Yeah, I would not call the reducing one. I would not call it A. Yeah, whenever I say A, it should be the original matrix. Otherwise, there's a confusion. Yeah.
Got it.
Like,
thank you.
Yeah. Okay, so this is A minus lambda I. So let me just first find out what this is. So this should be 1 minus 3, 1. Oh, okay, turns out to be very easy. Okay, so A minus lambda I turns out to be like identical 3 rows, right? So imagine that if you want to solve the null space, right? So it's really reduced to, I mean, you can directly see it. I don't need to say that what I'm going to do. It's really just only have 1 row left, right? You do the reduction. Okay, so reduction. So now I can easily see there's only 1 pivot. So, okay, so x2 would be alpha, x3 would be beta. I'm going to call the 2 free variables like this. And x1 would be, let me be careful, so 3x2 minus x3. So this would be 3 alpha minus beta. So my solution set in the null space will looks like 3 alpha minus beta, alpha beta. So first, just by looking at this is a typical format for your eigenvector, right? So essentially the solution set, the solution we are solving is one eigenvector or a format of eigenvector. Then you collect all of it, it becomes the eigenspace. That's our null space. So I want to be able to see what's the basis. So I'm going to represent it in terms of like a linear combination of 2 vectors. So alpha would be 3, 1, 0, and plus beta. This would be minus 1, 0, and 1, right? So you can see that then the null space of this A minus lambda I, or essentially you can call this is the eigenspace for the eigenvalue 1, right? So depends on how you want to express it. You can tell me what does it looks like in terms of the span, right? This is the span of these 2 vectors because any eigenvector or any solution in the null space looks like the linear combination of these 2 vectors. Or you can tell me alternatively, if I'm asking for the basis, then the basis consists of these 2 vectors. So you can see that in this case, my eigenspace is a 2-dimensional subspace because you have 2 vectors as bases, right? So yeah, so either way, you can either depends on what the question is asking. For example, in the homework, right? They might ask you the basis, they might ask you what's just the eigenspace looks like. So you can see that this is the first time actually in the example that we saw you could possibly have a 2-dimensional eigenspace, right? Back then, because we only have 1 eigenvalue, so you have one like 1-dimensional subspace. But here, because you have repeated eigenvalue here, so it's possible that you could have a 2-dimensional eigenspace. Okay, so the last thing I want to do before, I don't know whether I still have time to do the complex thing, but one thing I want to do is this thing that this is actually in generally true. And then I think one or two of the homework, you will need this. This is actually not hard at all. This is a property why we love eigenvalue and eigenvector. Because in some sense, you can think of eigenvalue and eigenvector, especially eigenvalue, I would say, it gives you it actually carry all the important information you need about this matrix. Okay, so what does that mean? So if you have, say, n by n matrix and you have n eigenvalues, here, when I say n eigenvalues, it included the repeated one, right? So you need to separate the repeated one as different count. And if you really look at what the characteristic polynomial looks like, then you can actually, because you know lambda 1 to lambda n are your root of this polynomial, right? So you can actually do the factorization. But it really depends on what n is. You might carry plus or minus sign. So in general, you can write down your polynomial in this format. But don't worry about it. I'm not going to ask you to memorize it. I'm just using it to prove my point. So if you plug in lambda equals 0 in this equation, then what's P of 0? P of 0 means you plug in lambda equals 0 in this polynomial. It actually gives you the determinant A on the right-hand side. And the left-hand side gives you the product of all the eigenvalues. So what does that mean? It turns out that it doesn't really matter what your matrix is, right? N by N matrix is. The determinant of this N by N matrix will always be the same as the product of all the eigenvalues. So in some sense, if you knew what eigenvalues are, right, all of the eigenvalues, then you know the determinant, right? That's why I say all these eigenvalues carry important information about determinant A. In other words, for example, if one of the eigenvalue is 0, then you right away know this matrix is not invertible, because if one of the eigenvalue is 0, then your determinant should be 0, right? So right away, you know that, oh, A cannot be invertible, or you can say it's singular. So you can see that by knowing the value of eigenvalue, you actually know a lot of information about this matrix. That's why eigenvalue is in some sense kind of carry like a very compact information about matrix. And even more, sometimes it's also useful to know this information. So there's another information carried by the eigenvalue. So first we can define what we call the trace of the matrix A. And what does that mean to be trace? Trace is really what we meant by just add up all the diagonal entries. So this is the sum of all the diagonal. So whatever you give me an N by N matrix, I add up all the diagonal entries, then it's called the trace of A. It turns out that this trace of A is also closely related to the eigenvalue, because the fact is the trace of this matrix A will always be the same as the sum of all the eigenvalues. Okay, so you can see that's why eigenvalue really tells you a lot of information, right? Like for example, you don't even have to like compute the determinant of A, right? You already, by knowing the eigenvalue, you know the information. So I'm going to use the very first example we did, and just to confirm this is the case, right? So remember the first example we did was this 2 by 2 matrix, and we found 2 eigenvalues, right? So let's double check, right? Just to convince ourselves this is the case. So what's the determinant of A, right? If you directly compute it, this is really just 3 minus 8, right? This is minus 5. But you can see lambda 1 times lambda 2 is also 5 times minus 1, which is minus 5. So really, we know that determinant A equals the product of all the eigenvalue, right? So I'm just doing a quick checking here just to show you that this is definitely the case. And what's trace of A in this case? Trace of A is the sum of the diagonal. It's 4, right? And I claim trace should be the same as the sum of the eigenvalue, right? So indeed, these two are equal, right? So you can see that, I mean, of course, you can do this for any matrix A, right? So it's possible that you could have, say, complex eigenvalue and eigenvector, right? So then in that case, you could have like you could also do the computation in complex value. So up to here, you already have all the information you need, for example, for the exam and also for the homework. So as I mentioned, I want to include the complex eigenvalue for the completeness for the material, because I really think there's a need to show engineer students that you could possibly have eigenvalue, which is a complex number. And the computation may be a little bit more involved because you need to deal with complex number. But I believe if you already, I think as most of the engineer student, including math student, you should already, at some point, not now maybe, like at some point you're going to take the differential equation class. And in that class, you're going to also encounter the complex number as well. So I don't think a complex number should be a serious issue, yeah, for everyone. As I said, I would not include the complex case in the exam, and I also didn't include it in the homework. So you don't need to worry about this, because I understand that this kind of computation may be a little bit complicated. But I want to at least show you a little bit of the knowledge of complex number, and then also to tell you that if you see complex number as the root of a polynomial, of a real number polynomial, then it actually has a nice property and shortcut. Okay, so after here, I mean, you already have everything for the exam. So I want to quickly go over the case for like complex eigenvalue. So first, in order to talk about this, then I need to tell you what a complex number is. Okay, if you already know a little bit knowledge, then you already seen this before, but I don't want to assume that's the case. So what's a complex value, right? So before we can talk about a general complex number, then I need to tell you this, what we call the imaginary number. We use this spatial notation. So this is not a real number. This is somehow what we call the imaginary number, because you can see, usually we say square root of -1 does not exist. So we call this spatial number to be I. This is the usual like imaginary number, the notation we use. And a complex number just simply means any number in this format, a plus b times I, while a and b are the usual real number we know. So for example, you could have 2 minus 3i. That's one type of complex number. Or you can have minus square root 5, right? I, right? You may not have the a part, right? Or possibly you could have something just looks like real number, right? Because you can think of real number as 4 plus 0i, for example, right? Then this is just 4. So we, in some sense, if you're talking about the general complex number, real numbers is a special case of complex number. In general, people would include real numbers into the complex number. Okay, so you could have all the possible complex number here. And what's the good property about this imaginary number I here? If you think about it, if we call I to be square root -1, then it will tell you I squared to be -1, right? Just squared it, okay? And you multiply another I again. So the I cubed will also be -I, right? You just multiply another I. And then you do it again, I to the 4th will be 1, right? Just keep multiplying by I. And then you will see that because once you got to I to the 4th, which is 1, you multiply by another I, it becomes just the original I. So then you can see that it starts having a cycle, right? So it's become periodic. So it's a cycle of 4, right? So that's why this imaginary number has this nice format, right? So you don't really need to keep writing as I to the 6th, I to the 8th, because you can actually reduce to any one of this case, right? So it's a cycle of 4 with this number I, okay? So there's some nice property. This property is going to help us to simplify some computation, right? For example, if you multiply 4 numbers, including I, you can somehow simplify it. Okay, so then what's the upshot here? It turns out that, okay, we were dealing with this matrix, right? In the case that when our matrix A has all the real number entries, then of course you can imagine if all the numbers in A, the matrix has real number, then the polynomial, characteristic polynomial that we want to solve is also has real coefficients, right? So then in that case, if this is the case, right, then we can prove like a very important property is that, for example, if you have some random real, like I'm just make up some example, like this is really not necessarily correct, but I'm just saying that, oh, like if you have some real coefficient like polynomial, right? Say you want to solve this equals 0. If you give me some random one, it's possible that your root could possibly be a complex number, right? Remember, like even just for the quadratic polynomial, remember when you maybe in high school college algebra, when you're trying to use the quadratic formula, right? There's an entry which looks like square root b squared minus 4ac, right? If you like just use the quadratic formula. And if the number under the square root is negative, in the past, we just say, oh, the real root doesn't exist, right? But now with this complex number, we can deal with the complex root, right? So it turns out that, remember, in the quadratic formula, you have this plus and minus. That tells you a fact that if you're going to see a complex root, it will occur in a pair, right? And this is what we call the conjugate pair. So if in this case, when all the entries of your polynomial is real numbers, when you're trying to solve the root, when you try to solve the polynomial equals 0, it's possible that you could see a complex root. But when you see one complex root is buy one, get one free, you will actually see a conjugate pair, okay? What does conjugate pair means? It means that if you see one of them looks like A plus BI, the conjugate, this is what we call the conjugate of lambda, and we use this bar as the notation. And it just really means that you change any number in front of I to be negative sign. So for example, if lambda equals, say, -2 minus 3i, then the conjugate of lambda would be -2 plus 3i. Then you might wonder what happened if it's just real numbers, right? If it's just only real numbers, right? So I want to say this note here. Let me skip to this note first. If you try to find out the conjugate of the real numbers, right? For example, if lambda is 2, then you should think of this as 2 plus 0i. Then the conjugate is really just 2 minus 0i, which is still 2. So real number, you can think of real number is a special case where conjugate will equals itself. Okay, so that's another property here. So why we care so much about the complex root to appear in conjugate pair? First of all, it's nice, right? As I said, once you find one, you find all of them. We find two, right? So it will always appear in the pair, right? So it depends on the degree of your polynomial. If you know you're going to have, if you see, for example, like if you know you're going to have in total four complex roots, then they should appear as two pairs, right? So that's why it's actually nice, because if you found one, you found another. So it should appear in a pair. Even better is this fact I put in red color. If you have, say, a complex eigenvalue lambda, and of course, you need to, again, solve the null space of A minus lambda I to find the eigenvector. So let's say you found one eigenvector for lambda. It turns out that not only eigenvalue will appear in the conjugate pair. So the first thing you know is lambda bar, the conjugate number, will be an eigenvalue. Even better, if you take this possible eigenvector with possible like a complex entry, then you take the conjugate of each entry. This z bar will also be an eigenvector for the conjugate eigenvalue. So you can see that the eigenvector also kind of appear in the conjugate situation. So basically this tells me if you can find me a complex eigenvalue lambda and the corresponding eigenvector, then you automatically found another complex eigenvalue lambda bar, and also the associated eigenvector for lambda bar, which would be just take the original eigenvector you found and take the conjugate. So that's why you have so many nice properties here. In some sense, you can do less algebra if you think about it, right? For the complex case. So now I'm just going to show you quickly how to solve this. I'm guaranteed that you're going to see the complex eigenvalue. So first of all, again, I'm going to solve the eigenvalue. And you can see that this time you're going to see the complex situation. Okay, so I want to solve this equals 0, determinant of A minus lambda I. So this is the case. Okay, so I'm going to have 1 minus lambda squared plus 4 equals 0. So let me expand this to find the root. So this will be lambda squared minus 2 lambda plus 1 plus 4, that's 5. Okay, so you can see that just stare at this for 10 seconds, you probably realize that there's no way you can do a nice factorization. And this is when you should use the projective formula. Okay, so projective formula. If you forgot what projective formula is, please definitely you want to review this. Okay, so I'm just going to tell you what you're going to see here. So this is 2 times 1, right? 2 times A and minus B plus and minus B squared. Oh, sorry, B squared, that's 4 minus 4 times 5. Okay, so I'm using the projective formula. Okay, so let me simplify this a little bit. So I have 2 plus and minus. Under the square root, you have 4 minus 20. That's minus 16. As you can see, that's where the real root does not exist, right? So in the past, when we see this number to be less than 0, we will say, oh, real root does not exist. But this time, because the imaginary number I, it allows us to deal with a situation like this. But how are you going to solve it, like explicitly, right? So you can see that, okay, what I'm going to do is I'm going to break this minus 16 into, so I have square root of minus 16. So I'm regarding it as my square root 16 times square root minus 1, right? I want to come up with this I. Okay, so now I have essentially this is 4, right? 4 times I. And please do the algebra step by step carefully, right? So I can simplify the 2 here. So this would be 1 plus minus 2i. As you can see, by using the projective formula, pretty much your complex eigenvalue should be appear in a pair. And the conjugate pair essentially already kind of reflected in your projective formula, right? So you don't really have to look for it. When you solve the projective formula, it's already there, right? So you have 2 complex eigenvalue, right? So you can say the first one is 1 plus 2i, and second one is 1 minus 2i. And you can see this is really, the second one is the conjugate of the first one. Okay, it's already in a pair. Now the only issue is, okay, now we need to look for the null space, the eigenspace, right? So I'm going to just do the computation here. So for the eigenspace, for the lambda 1, right? So I'm looking for null space of A minus lambda I. Okay, so this could be a little bit tedious because then you will have all this eigenvalue involved, complex value involved, right? So let's just see it for once, right? So let me carefully calculate this. So my original matrix is 1, 2, minus 2, 1. But I want to subtract this eigenvalue from the diagonal. So 1, 2, okay. Okay, so I'm going to solve this, right? So, okay, let me not put in this for now. Okay, so 1 minus 1, so this should end up with minus 2i2. And yeah, same thing here, minus 2i. Okay, so now you can see that because you're involving the complex entry here, so when you're trying to do the row reduction, you could possibly use the complex value. Okay, so you should simplify this, right, a little bit more. So I'm going to simplify this just by dividing the first row by minus 2. I mean, there's so many ways you can do this. And then also, like, I'm going to actually, I want to divide by minus 2. And same thing here for minus 2, just to make it slightly easier. So this will be minus 1 here, and this would be 1 and I, right? Okay, so I want to solve this equals 0, right? I want to solve the null space. Okay, so now let's see. So one thing I can do to even simplify more is that this is actually, this is a little bit tricky in the algebraic sense, right? That's why I didn't want to really include it in the exam, because it's really takes a little bit time to solve the algebra. So you can observe that if you take row 2, because there's a 1 here, and multiply by minus I and add it to row 1, you're going to see that you can cancel out this I here. And if you take I times minus I, this is going to be 1. So you could actually, turns out that if you observe this, these two rows are a complex multiple of each other. So you could possibly do a reduction using complex number. Okay, this is okay in this case because we have a complex eigenvalue. So now I'm just make it like swap the row. So I have 1i 0 0. Now I can really solve the solution. So x2 will be alpha. x1 plus I equals 0. Plus I times x2. Sorry, will be too fast. So this tells me x1 is minus I x2, which is minus I alpha. Okay, so my solution really looks like minus I alpha times n alpha. So you can see that the basis in this case would be minus I and 1, right? And be careful, right? When we talk about basis, your way of solving it could be different than mine in the sense that, for example, back then, if we say the basis is 1, 1, right? You could pick a different basis, right? You could pick 2, 2 as long as it's multiple. So when you do the homework, if you notice that your answer, your basis that you choose differed with the answer or with the solution in the back of the textbook by some multiple number, don't panic. It's okay, right? Because basis is not unique, right? You can say that 1, 1 is the basis for my one-dimensional subspace. You can say 2, 2 will be a basis, right? Because they're going to span the same space anyway. So your basis could be a multiple differed by a multiple, right? So in this case, my null space, right, of A minus lambda I in this case, or the eigenspace, is essentially the span of this complex vector, right? This is the Z I was talking about, if you want to call it. This is one of the complex eigen vector I can talk about. And of course, you can say that's the basis, right? So basis is minus I and 1. Okay. But now, in the end, this is the eigenspace for one of them, right? What about the other? But as I said, for the complex eigenvalue, it's not too bad at all. Once you found lambda, once you found one of the eigenvector, they all appear in the conjugate pair. We already know what's the other complex eigenvalue. So all you need to do is take the conjugate of this eigenvector you just found. Then that will become the eigenvector for my lambda bar. So that's actually really like a bonus for us. So for lambda bar, right, which is the second eigenvalue, this is the case for 1 minus lambda, right? So we take so if we say we already know that this vector Z, which is minus I1, is an eigenvector for lambda, right? So we know that Z bar should be an eigenvector for lambda bar, right? So what's Z bar? So Z bar means you take conjugate for this vector, which means you take the conjugate for each entry, right? So for minus I, you need to switch the sign, right? It becomes plus I. And as I said, if you take the conjugate of real number 1, it should be itself. So this is plus I and 1. So it turns out the conjugate of Z, the Z bar is just I and 1. So right away, you can tell me that, okay, I and 1 is my eigenvector, right? So basically, you can say the eigenspace of lambda bar is this like span of I1, or you can say the basis is I1. So you can essentially right away by taking the conjugate to find out what's the corresponding new eigenspace for the other conjugate complex value. Okay, so this is just a little bit extra. So I want to show everyone that this is what you could possibly encounter in general, right? Because in the realistic case, it's not always the case that you will only have real eigenvalue, even though I only test the real eigenvalue situation. But you could possibly still see a complex eigenvalue. And actually complex eigenvalue in some sense have a better property, right, than the real one. Okay, so as I mentioned, please read the announcement, and I will do like a pretty thorough review on Thursday, so you don't want to miss Thursday's class. And please start working on the review notes I already posted. All the review material are already there. I posted a review note with a lot of example. I posted this extra textbook exercise I pick in the folder I usually put. I also upload a list, which is I think 1 or 2 pages, I don't remember. It's just a list of topics and sections, including all the topics that I have mentioned, we have learned in this class before. So it's just kind of like a checklist for you to see kind of like, oh, like we touched this and this and that. You can kind of just, I mean, kind of do like use it as a, I don't know, review or something like that. So I post several things there. They all are all under the manual practice, the practice problem, something like that. So yeah, please go there to check it. And for the Thursday's review, after the review, I will post the review notes right away in where I usually post the lecture notes. And the video, hopefully they will upload the video as soon as possible. So yeah, so let me know if you have any question regarding the exam or homework. Or don't forget, I have office hour tomorrow from 1:30 to 2:30, so you could stop by. If you can't, please make an appointment with me.
Have a good day.
You too. Okay, so I'm going to end the recording.